Telling you about Kähler geometry of complex manifolds. So the plan for today is to finish talking about the Kähler holonomy groups, which are U of M, SUM, SPM. And then for tomorrow on Wednesday, I want to talk about the exceptional holonomy groups G2 and spin 7. I haven't actually allocated any time to talk about the holonomy group SPM, SP1, but if you want to ask me questions about that later, I could fill that in a little bit. Okay, so I want to start with a section 3.6 on Richie curvature of Kähler manifolds. Okay, so if we let X and J and G be a Kähler manifold, and R lower A, B, C, D, the Riemann curvature of G. Well then, well at each point, you have, you can think about the curvature tensor as lying in the symmetric tensor product of H with itself, where the AB indices lie in one copy of H and the CD indices lie in the second copy of H, where curly H is the Lie algebra of the holonomy group of G, which is contained in U of M, since G is Kähler. So hence curly H is contained in little um, the Lie algebra big um, which may be identified with the vector space of real 1-1 forms. On X. So therefore the indices AB and the indices CD, sorry, perhaps I should have started later, in R, A, B, C, D lie in the real 1-1 forms. Okay, so as a tensor on a complex manifold, we know that the Riemann curvature is antisymmetric in A and B and antisymmetric in C and D. What this tells us is that it's also compatible with the complex structure J, in that it's of type 1-1 for those two, of type 1-1 for those two. So then if you use this, we can show that the Richie curvature which you can write as R lower AC is G upper no, let's say R lower BD is G upper AC R A B C D. So you take the trace using the metric of the first and third index. This is a tensor of the same type as G. You have, well, it's symmetric, as a Richie curvature always is, but it has R lower AB is J, lower A upper C, J lower B upper D, R C D. So that is its Hermitian. Well, apart from it's just a Hermitian tensor. And RAB is RBA. Okay, so that's compatibility between the Ricci curvature and the complex structure. Okay, now for the metrics, for the metrics of Hermitian type, we could turn the metric into a 2 form using J. We can do exactly the same thing for the Ricci form, Ricci metric. So the Ricci curvature, we can turn it into a 2 form. So as for Kähler forms, we can define a 2 form rho by rho lower AC is J upper AB R lower BC, which is called the Ricci form. So it has the same relationship to the Ricci curvature as the Kähler form has to the Kähler metric. And this is a real 1,1 form. Okay, well, so the Kähler form is closed. It turns out that the Ricci form is also closed because the second Bianchi identity the second Bianchi identity tells you something about the derivative of the Riemann curvature, and this now then implies something about the derivative of the Ricci form. The second Bianchi identity implies that d of rho equals 0 as for Kähler forms. Okay, so you can also recover the Ricci curvature from rho just by multiplying rho, let's say on the right, by J. And so therefore, if you know rho, you also know the Ricci curvature. Okay, well, so here is a way to understand the Ricci form. So if M is the complex dimension of X, then we consider the bundle of M0 forms, lambda M, 0 of X. So these are not top dimensional forms in terms of real manifolds. These are actually middle dimensional forms. So the forms of type M0. So there's a name for this, and the notation is called Kx and called the canonical bundle. We could also write it as the lambda M C of the bundle of 10 forms on X. So this is a holomorphic line bundle on X called the canonical bundle. It's something which is very important in algebraic geometry. And the metric G on X induces a metric in the sense of a metric on the fibres. So each fibre of kx, which is C, gets a metric. So you know the kind of lengths of M0 forms. It induces a metric and a connection on the canonical bundle kx. And the connection has structure group U of 1, because it's preserving it's a complex one-dimensional vector fibres with metrics, and U of 1 is what preserves that. So hopefully UG has told you all about bundles on connections on bundles with structure groups. Okay. But because U1 is abelian, the curvatures of U1 connections are particularly simple to understand. But the curvature of a U1 connection is just a closed 2 form. In fact, the Richie form is the curvature of the natural connection on kx, possibly up to sign. I haven't checked that recently. This helps us to know the cohomology class of the Richie form in de Rham cohomology. So this enables us to identify the de Rham cohomology class of rho. So we have square brackets rho is 2 times pi times C1 of x, where so C1 of x, which is actually minus C1 of kx. The minus is because the kx is, well, C1 of x is by definition the first Chern class of the tangent bundle, and this is derived from the cotangent bundle, and the minus sign is because of the duality between the cotangent bundle and tangent bundle. So this is the first Chern class. So I'm not going to talk about characteristic classes very much. Has UG told you about these kinds of things? No? Okay, in that case you'll have to remain ignorant. Okay, so this is a topological invariant called a characteristic class. Okay, so characteristic classes are topological invariants of line bundles and vector bundles which live in cohomology. If you want a basic reference on them, there's an old book by Milner and Starchef, characteristic classes. Or you can find I presume you can probably find a survey paper on them which would be simpler, but so And this is something which depends only on the complex structure, or really the almost complex structure, up to isotopy. And well, in fact, C1 of x lies in the integral homology H2 of xz. But so it's really a discrete thing. It doesn't change under deformation. Let's say of the complex structure, but we take its image in H2 of x R, which is the same as H2 of de Rham cohomology. Okay. So the cohomology class of the Richie form doesn't depend upon the cohomology class of the Kähler class. The cohomology class is the Kähler form. It depends only on the complex manifold X and J in some topological way. Okay, so also note that G is Richie flat. Well, if and only if RAB equals 0. If and only if the Richie form rho is 0. If and only if the connection on Kx is flat, because curvature being 0 is just by definition means that the connection is flat, and this is only possible if C1 of x equals 0. So we're going to be interested in Richie flat Kähler metrics because they're more or less the same thing as Kalabi-Yau. They include the Kalabi-Yau and the Hyper-Kähler cases. And so the condition that C1 of x equals 0 as a topological condition on your complex manifold is going to be very important. Okay. We're now going to go on and talk about the Kalabi conjecture. So this is not a conjecture anymore, it's a theorem, but it's still usually called the Kalabi conjecture. And it concerns the Richie curvature of Kähler manifolds. So we'll have a section 3.7 on the Kalabi conjecture. Okay, so, well, here it is. The Kalabi conjecture. Which I should think should probably be better be called the Oban Kalabi-Yau theorem. So let's take X and J to be a compact complex manifold. And G, a Kähler metric on big X with Kähler form omega. So now let's suppose that rho primed, so rho is going to be the Richie form of G. Let's suppose that rho primed is some other, a real closed 1,1 form. So with de Rham cohomology class, square brackets rho primed equals 2 pi C1 of x in the second de Rham cohomology group of x. So rho primed is a candidate Richie form for some Kähler-metric on x, because it has the properties we need. It's real, closed 1,1, and it has the correct cohomology class. So the conclusion is that then there is a unique Kähler-metric G primed on X with Kähler form omega primed, satisfying two conditions. So such that, firstly, G primed has Richie form rho primed, and the second condition is that bracket omega primed equals brackets omega in the second de Rham cohomology of X. Okay, so this is true. So you don't need to express it saying by choosing some Kähler-metric first. You could just say, suppose rho primed is a real closed 1,1 form, then in every Kähler class there is a unique Kähler-metric G primed with Richie form rho primed. I've just written it this way because it's going to relate nicely to the way I'm going to explain the proof. Okay, so well, a few comments on this. So this tells us about the existence and uniqueness of Kähler-metrics with prescribed Richie curvature. So, if you give me any plausible Richie curvature for a Kähler-metric on X, I'm supposed to find a Kähler-metric which has exactly that Richie curvature. And then in each Kähler class there's only one. And well, so you know that the family of Kähler classes is the Kähler cone, which is some finite dimensional open cone in the 1,1 part of de Rham cohomology. So then you'd actually get there'd be a family of Kähler-metrics parameterized by the Kähler cone with that Richie curvature. Okay, so it was, well, the conjecture was posed by Kalabi in 1954. Actually, Kalabi screwed up. Initially, he published a proof of the Kalabi conjecture. So he published it as a theorem, and it was fairly soon realized that there was a gap in the proof. So then it became known as the Kalabi conjecture. And theory Oban made some fairly major progress on it, but the thing wasn't actually sorted out until Yau in 1976. So I think Oban and Kalabi and Yau all deserve credit for the proof, but Yau's basically managed to get his name on it. People will say Yau's proof of the Kalabi conjecture because Yao's good at that kind of thing. But I know Yao basically did the last little bit of the proof, as it were. The overall structure of the proof is due to Kalabi, and Oban did some important stuff in the middle. Okay, so the thing we particularly care about is a case in which rho primed is 0, which of course forces C1 of x equals 0, because then you can produce a calorimetric with 0 Richie curvature. So let's state this as a corollary, and then I'll talk about the proof of the Kalabi conjecture. Okay, so when rho primed equals C1 of x equals 0, we have corollary, which is, well, let's suppose that X and J is a complex manifold. So the compactness is important. So there are versions of the Kalabi conjecture involving non-compact complex manifolds, but they always have to prescribe somehow the geometry of the Kähler manifold X and J and G at infinity in some fairly strong way. You can't just do a Kalabi conjecture for kind of arbitrary non-compact Kähler manifolds, because you lose both the existence and the uniqueness in the problem, and there'd be nothing left. Okay, so X and J is a compact complex manifold with C1 of x equals 0 in real cohomology. This would allow C1 of x to be torsion in integral cohomology, because the map from integral cohomology into real cohomology is not always injective. So then every Kähler class on X contains a unique Ricci flat calorimetric. Of course, the assumptions don't say that X admits calorimetrics. If X doesn't admit calorimetrics, then there aren't any Kähler classes, so the statement is vacuous. So here, at least depending on your definitions, because so if you look in the literature, you'll find a number of different non-equivalent definitions of Kalabi-Yau manifold going on. So Ricci flat Kähler manifolds are basically Kalabi-Yau manifolds, although I'll give a definition a bit later, which will be a Ricci flat Kähler manifold which satisfies some extra conditions. So we will discuss them later. So this corollary is going to be our technique for producing examples of Kalabi-Yau manifolds. You have to find a suitable compact complex manifold with C1 of x equals 0, which you do using algebraic geometry, and then this Kalabi conjecture result would tell you can find the Ricci flat calorimetrics. So it's also worth noting that this is just an existence result. You can't actually write down these calorimetrics G primed, and in fact they're almost never actually known. So You just know that there exists some metric G primed. You can't write down a formula for it or what it. Get very much control of what it actually looks like. Okay, so let's give a sketch proof of the Kalabi conjecture. Right, so as in the statement of the conjecture, let X and J and G be compact scalar with scalar form omega and Richie form little rho. And let's suppose rho primed is a closed and real 1-1 form. With the Riemann cohomology class, square brackets rho primed is 2 pi times C1 of x. Well, so then the cohomology class of rho primed is a cohomology class of rho, because rho is actually a Richie form, and therefore it has the Riemann cohomology class 2 pi C1 of x. So therefore the Riemann cohomology class of rho prime minus rho is 0, and it's exact real 1-1 form. And now we can apply the DD bar lemma. So we get that rho primed minus rho is I d d bar of f for f going from x into r smooth and unique up to addition of a constant. And this is by the global d bar lemma. So remember the d bar lemma I told you about on Friday. It had two parts, one of which concerned small open sets in C to the m, the other of which concerned compact Kähler manifolds, like this one. Okay. Now let's fix the constant C by requiring that the integral over x of e to the f times omega to the m is equal to the integral over x times omega to the m. So you'll see why I want this equation in a minute. So this is m factorial times the volume of x, so that's a positive number. That's also a positive number as you're integrating a positive function over x. So the two positive numbers are, their ratio is a positive number, the log is a real number, and so basically we add on, if we choose some initial f, we add on the log of the ratio of that to, or minus that to f, and we can arrange this is true for some unique active constant c, so that fixes f uniquely. here M is the complex dimension of X. Okay. So, well, we seek a calorimetric G primed with Kähler form omega primed in the same Kähler class as G primed, as G rather. So, well, again by the DD bar lemma, we can write omega primed is equal to omega plus I d d bar phi, where again phi going from X into the reals is smooth. Well, phi is unique up to phi goes to phi plus c for given G primed and omega primed. And let's fix the c by requiring that the integral over x of phi times omega to the m is 0. So that's not really crucial. It's nice to have uniqueness in your problem. Okay, so we want some function, smooth function phi, such that this thing is going to be a Kähler form with the correct Richie curvature. So the condition that G primed has a Richie curvature rho primed turns out to be equivalent to omega primed to the m is equal to e to the f times omega to the m. Okay, so in other words, we prescribe the volume form of G primed. Okay, so the volume form of G primed is omega primed to the m divided by m factorial, which is that over m factorial. So, okay, so you can now see why I ask for this to be true, because if omega prime to the m and omega to the m are, well, if omega prime and omega are in the same cohomology class, then omega prime to the m and omega to the m are in the same cohomology class, which means that the integral of these two forms have to be the same. So it's necessary that this equation should hold for that equation to hold with omega prime and omega being cohomologous. Okay, so yeah, and you can think about the Kalabi conjecture in terms of existence of calorimetrics with prescribed volume forms rather than calorimetrics with prescribed Richie curvature. And that's actually kind of nicer because you've deleted two derivatives in the problem by doing this, because the the Richie curvature is really a kind of second derivative of this equation. So we've made a double integral. Okay. Okay. So we must solve the equation omega plus I d bar phi. That's a real 1-1 form to the power of m. So we wedge it with itself m times. That gives you a 2m form, which this is now equal to e to the f times omega to the m. Okay, so this is an equation in real 2m forms on our manifold. And this is a nonlinear second order and elliptic PDE. Okay, so f is given. It's something you recreate from the Richie form you're trying to make. Phi is what you've got to find. So we've got to solve this equation for phi for given f. And well, so it's non-linear, but if you linearize it around the case in which phi and f are small, so if phi and f are small, it is approximately the Laplacian of phi is f, where delta is the Laplacian of g, so this is really d star d. Okay, so now actually we know a lot about how to solve, well, about the existence of solutions of the Laplacian of phi as f on a compact manifold. In fact, if the integral of f is 0, then a solution phi exists, and the solution phi is unique provided the integral of phi is 0. This fixing the constant here, if f is small, then this approximates being the integral of f being 0, and I've got the integral of phi being 0 here. So those two conditions there, if f and phi are small, are essentially the conditions for the existence of a unique solution there. Okay, so this is an equation of a type called a Monge-Ampere equation. You could think about, well, this is kind of a matrix of second derivatives of phi, and this raised to the power of m is basically a determinant of an m by m complex matrix. So it looks a bit like the determinant of the identity plus the matrix of second derivatives of phi is equal to some prescribed function there. Okay. So we're going to solve, or Oban and Kalabi now solve this using something called the continuity method. So you basically produce a one-parameter family of equations like this, where depending upon t is 0 up to 1. When t equals 0, you know what the solution is. When t equals 1, the problem is a problem you want to solve, and then you show that you can essentially deform a solution to the easy problem to a solution of the hard problem. So let's call this equation star. So we solve star by the what's called the continuity method. So for t in 0 up to 1, let's consider the equation omega plus I d bar phi t, the power of m, is e to the t times f. Actually, we're going to need to to add on a constant, which I'll write Ct times omega to the m. And let's call that equation star t. So I've basically inserted a t in front of the f and then a correcting constant. So where Ct in the reals is chosen such that the integral over x of e to the t times f plus Ct omega to the m is the integral over x of omega to the m. Again, that's a necessary condition for this to have a solution. And let's say we also want integral over x of phi t times omega to the m is 0. So that's a one-parameter family of problems where t equals 1, you'll get C1 is 0, and this reduces to star. So let big S contained in 0 up to 1 be the set subset of t in 0, 1 such that equation star t has a solution. And well, then, firstly, 0 lies in S with phi 0 is 0, because then you just get thing equals thing. Omega to the m is omega to the m. And if 1 lies in S, then the solution phi 1, which is phi, solves the Kalabi conjecture. So what we want to do is we want to prove that S is both open and closed. So we prove that S is open and closed. So it's connected, and then S is all of 0, 1 because it contains 0 and 0, 1 is connected, and so 1 lies in S as we want, and the proof is finished. Okay, so well, the openness of S is fairly easy.
You're defining this one-parameter family of phi so that phi 1 is the phi you're interested in.
Yes, that's right. Yeah. So if when t equals 1, the C1 is 0, so that gets an e to the f omega to the m. That equation star 1 is this equation star over here. Okay, so openness of S is easy, or fairly easy, and it's proved by Kalabi. Using basically standard elliptic theory. And Kalabi also proved the uniqueness of any solution phi t to this thing, provided it exists. And so then the closedness is more of a problem. So for closedness, you want to prove that S is closed under limits. So to prove S is closed, we need a priori estimates things that say that basically bounds on all solutions of star t in the Banach norm C3. So what you want is a statement that if a solution star T exists to this, then the C3 norm of phi T is less than or equal to some constant big C, depending upon the geometry of the problem, but not depending upon the choice of solution. So then, well, when we take a sequence Ti in S, then a subsequence of the phi Ti's converges, or maybe not in C3, but in some C2 comma alpha, let's say, and then the limit is a, well, let's say with Ti goes to T, limit is a solution phi T to star T. And that would then, so then S contains its limit points and is closed. Okay, so then these a priori estimates, they're the kind of most difficult part of the proof, and well, so I think that maybe the north, onth, and tooth estimates were done by Kalabi and Oban, and the Yao did the third order, the third order a priori estimates, which are the thing which nobody else could solve. Okay, so perhaps that's all I'll say about the Kalabi conjecture.